Picture this. You've got a massive, state-of-the-art piece of electrical equipment. It's been tested, it works perfectly at sea level. Now, take that same machine, haul it thousands of meters up a mountain, and flip the switch. All of a sudden, it starts failing in really dangerous, unpredictable ways. So what's going on? The machine hasn't changed, the mountain has.
So, let's dig into this mystery. What do these two places really have in common? I mean, one's looking up at the stars, the other is digging deep into the earth. But you know, they're often built in these crazy high places. We're talking Chile, Peru, the Tibetan Plateau, and because of that, they share a common invisible enemy.
And that enemy? It's the air itself. Or, to be more accurate, the lack of it. The super thin atmosphere at high altitudes just can't protect and cool high-voltage gear the way dense sea-level air can. And that can lead to these catastrophic failures that shut down an entire operation. Okay, so how exactly does less air cause more problems? It's not just one thing. It's actually two different physical phenomena happening at the exact same time, and both of them come from the simple fact that the air up there is way less dense. This is the 1-2 punch at the heart of the problem. On one side, you've got insulation failure. See, air is normally a fantastic electrical insulator. But when it gets thin, electricity can literally jump across open gaps. Sparks, shorts, you name it. On the other side, you've got cooling failure. Air is also what carries heat away from hot parts, but thin air is kind of like a weak little fan. It just can't get the job done, and things start to get dangerously hot. Let's focus on that first problem, the insulation. The key concept here is something called dielectric strength. The best way to think about it is like air's electrical armor. At sea level, that armor is super thick and strong, but as you climb higher and higher, that armor just gets weaker and weaker, making it way easier for high voltage to punch right through.
And the physics behind this is actually pretty cool. They call it an electron avalanche. At sea level, air molecules are packed in tight, so a stray electron can't really get going before it bumps into something. But in thin air, there are these huge gaps. That same electron can accelerate like a car on a totally empty highway, slam into an air molecule with enough force to knock more electrons loose, which then take off and hit others. You get this explosive cascade of energy that we see as a big spark or a flashover.
And this is not just theory, okay? The real-world consequences are serious. We're talking field reports from the Tibetan Plateau showing equipment failing at voltages 25 to 30% lower than what it was designed for. That is a massive and frankly dangerous drop in performance, all because of thin air. All right, now for that second problem, heat. Since thin air is so bad at carrying heat away, engineers have to do something called derating the equipment. That just means they have to intentionally run it at a lower current to keep it from overheating. So for example, a device that's rated for 400 amps can only be safely run at 328 amps once you get up to around 3,500 or 4,000 meters.
Just think about what that really means. You lose almost a fifth of your machine's power capacity. An 18% loss just from a change in altitude. You paid for a 400 amp machine, but the mountain is only going to let you use it like it's a 328 amp machine.
But here's the plot twist. The absolute heart of these machines, this component called a vacuum interrupter, is totally immune to all of this. Why? Well, because it's already sealed in a near-perfect vacuum. The pressure inside is always the same whether it's at sea level or on Mars. This tells us something huge. The problem isn't the core technology, it's everything around it that's exposed to that thin mountain air. So if you can't change the air, you have to change the equipment. And this brings us to the engineer's playbook, the strategies they use to design power systems that can actually survive and even thrive at high altitudes. So there are two main ways to go about it. The first is basically brute force. Just oversize everything. If you need 400 amps of performance, don't buy a 400 amp machine. You buy a 500 or maybe even a 630 amp machine. It's just built beefier so it runs cooler and has more insulation built in. The second strategy is to enhance it. You add stuff like powerful fans and bigger heat sinks to actively force that extra heat away.
Here's what that oversizing strategy looks like for voltage. A system that just needs 12 kilovolt insulation at sea level. Well, at 4,000 meters, it needs insulation rated for 17.5 kilovolts, and at 5,000 meters, a whopping 24 kilovolt. You're basically buying insulation for a much more powerful system just to get reliable performance.
And you know, this isn't guesswork. It's a super methodical process. Engineers follow this strict checklist. First, they get the exact site conditions. Then, they calculate the precise derating that's needed. From there, they pick their strategy: oversize or enhance. And this is crucial. They check everything.
down to the tiniest little part, to make sure it's also rated for altitude, because a chain is only as strong as its weakest link, right?
So what does this all look like in the real world? Well, the field reports from these remote places are pretty fascinating. They paint a really clear picture of this invisible battle that's going on against the thin air.
Okay, get this. At altitudes over 3,500 meters, engineers have actually reported seeing a characteristic purple glow on electrical connections at night. That glow is called a corona discharge. It's the air itself starting to break down under all that electrical stress. It's this beautiful, kind of eerie, and very clear warning sign that a dangerous flashover could happen at any second.
And on the heat side of things, the evidence is just as dramatic. Thermal cameras at some of those Peruvian mines have shown that the exact same parts, under the exact same load, run 15 to 25 degrees Celsius hotter than they do down at sea level. That kind of extra heat just accelerates wear and tear, it loosens connections, and it's this constant threat to the whole system's reliability.
So let's wrap this all up. Air is this silent, absolutely critical part of our electrical world. It's both an insulator and a coolant. At high altitudes, it does both of those jobs pretty poorly. And while the core tech is safe inside its little vacuum, engineers have to fight back against the thin air by either oversizing equipment or adding extra cooling, all while battling these very real effects like eerie purple glows and extreme heat.
It really makes you think, doesn't it? We just went deep on the effects of thin air, but this is just one example. It leaves you with a much bigger question. What other invisible environmental forces, like crazy humidity or a corrosive salt spray from the ocean, or even solar flares, are engineers constantly fighting behind the scenes just to